let's continue our story about the constructibility of the n-gon. Previously, we have linked this geometric problem to algebra by defining constructible numbers. Then we even gave a criterion for constructibility, namely alpha is constructible over Q if and only if it lies inside some extension K of Q, for which there exists a chain of quadratic subextensions. So that's the algebraic formulation of the constructibility of a distance alpha. But how about the constructibility of an n-gon? Well, that's going to be equivalent to the constructibility of the nth roots of unity. Why is that? To see why that is, we need to leave the real plane and look at the complex plane. Observe that the regular n-gon could be realized in the complex plane by taking the vertices to be the nth roots of unity. That is why we also call this constructibility of the n-gon the problem of dividing the circle into n equal parts. So our plan is as follows. In this video, we're gonna prove the necessary and sufficient condition for the regular n-gon to be constructible. Then in the next video, we're gonna give some explicit example. That is the part that I think is really beautiful and deep. So if you only have time for one video, I would pick that one. It makes explicit the idea in this proof. So from the example, you could figure out what the proof should be anyway. But let's not get ahead of ourselves. Our immediate task now is to prove the necessary and sufficient condition for a regular n-gon to be constructible. Now, previously we said that the constructibility of the n-gon is equivalent to the constructibility of the nth roots of unity. But wait, what does constructibility of the nth root of unity mean? We only talked about constructibility of real numbers. Well, here we're thinking of the nth roots of unity as corresponding to a point in the complex plane. So its constructibility is just equivalent to the constructibility of its real part. Our task now is to turn this into an algebraic condition involving only n. To that end, let's recall the algebraic condition for a number to be constructible. Remember that alpha is constructible if and only if it lies in some field extension K of Q, for which there exists a chain of quadratic extension. From our previous discussion, we then see that the regular n-gon is constructible if and only if the real part of the nth root of unity has a chain of quadratic subextensions. Now, observe that Qx has this decomposition into a chain of quadratic extensions if and only if this cyclotomic field itself has this decomposition. That is simply because the degree of this extension of the cyclotomic field over this Qx is going to be equal to 2. So if we have a chain like this, we can always add this field to the end of the chain and get a chain still of quadratic extension. Now, why is this extension of degree equal to 2? To see that, observe that as x is the real part of this zeta n, we can recover x by adding zeta n to its conjugate. On the other hand, we know that the product of zeta n with its conjugate is equal to 1. Putting those together, that means that zeta and its conjugate are roots of this polynomial. And now observe that this polynomial has coefficient in Qx. Thus the degree of this extension must be less than or equal to 2, since zeta n is the root of a quadratic polynomial over Qx. Now, can it be 1? Well, if it's 1, then that means these two fields are going to be equal. But that's not possible, because Qx is real, whereas Q zeta n is imaginary. So this degree can't be 1, and thus it must be 2, as claimed. Now coming back to our problem about constructibility, this now gives us this direct equivalence. Thus we have that the n-gon, the regular n-gon, is constructible if and only if there is a chain of quadratic subextensions of this cyclotomic field. It now remains to turn this condition into some algebraic expression involving n. To that end, we need to use the following fact about cyclotomic extension. Recall that every n cyclotomic extension is Galois of degree phi n, where phi here is the Euler phi function. And that's how we're going to get an algebraic condition on n, by passing through the degree of this extension. So, what can we say about this degree if this holds, if we do have this chain of subfields? Well then, by Taylor law, this degree is just going to be a product of these degrees, which are all equal to 2. So it must be a power of 2. Great, so we have a necessary condition. Now let's see whether the other direction holds true. Well, it does look suspiciously like a theorem in group theory. The theorem says that if G is an abelian group of order a power of 2, then G must have a chain of subgroups whose consecutive indices must be 2. This 2 theorem looks very similar, but this one is about field though. How do we relate field to group? Well, of course, the canonical answer is via Galois theory. How about we try applying this theorem for G equals to the Galois group of this cyclotomic extension. Let's check if it satisfies these hypotheses. First, is G abelian? Yes, indeed, we even know what it is. So that is checked. Next, is the order of G a power of 2? Yes, again, because the order of this Galois group is just going to be equal to the degree of this extension, because it's Galois. Therefore, this hypothesis is also satisfied. Thus, we must have this decomposition for the Galois group. Now, by Galois correspondence, this means that we have the following decomposition of subfields. So indeed, if this degree is a power of 2, then we have this decomposition, and in particular, the regular n-gon is constructible. Putting this and the previous discussion together now gives us an if and only if condition. We see that the regular n-gon is constructible if and only if the degree of this cyclotomic extension is a power of 2. And if you work this out using the definition of the Euler-Phi function, then you'll see that that's equivalent to n being a product of a power of 2 and Fermat primes. That is the gist of Gauss' proof of the constructibility of the n-gon in his arithmetic investigation. Now the proof might sound a little bit abstract and formal, but if we follow the idea underlying it, then we can actually give explicit construction. Those are really beautiful stuff, and we'll discuss that in the next video.